Great to be here to share our work titled Batch PIR and Label PSI with the Oblivious Ciphertext compression. And this is joint work with Alexander Bienstock, Sarvar Patel, and Kevin Yu. So in this work, we actually study two problems called the Oblivious Ciphertext compression and the Oblivious Ciphertext decompression. So we'll first go over what each of these problems are. And in the Oblivious Ciphertext compression problem, we have two parties, client and the server. And essentially, let's assume that the client and the server participates in some cryptographic protocol. And in the end, suppose that the server obtains some vector of ciphertext that's encrypted by the client's secret key. And in fact, for the rest of this talk, we actually assume that all the ciphertexts are encrypted using homomorphic encryption schemes. And that's going to be labeled as gray shaded blocks, and we'll actually use the white blocks as a plaintext for the rest of this talk. So the server at this point contains a vector of a length n ciphertext, and essentially the goal is to basically send this to the client. So the client basically wants to retrieve this data from the server, and it turns out there's some special properties of this ciphertext. There are actually some of the relevant entries are actually relevant that the client wants to retrieve. So in this case, these are actually colored blue in the slides. And the rest of the entries are actually irrelevant entries, and these are colored red. And another special property about this ciphertext is that all these irrelevant entries are actually encrypted as 0. And the server knows at this point that there are exactly k relevant entries, and the n minus k irrelevant entries are 0, but it actually knows no other information at this point. On the other hand, client actually knows exactly the indices of the entries that it wants to retrieve. So these are the relevant entries that the client wants to retrieve, and in this case, 1, 3, 5 indices. And the goal is to essentially send this, and then retrieve the corresponding relevant entries from the server. But obviously, these zero encrypting ciphertexts are wasteful in terms for the communication purpose. So the goal essentially is to basically reduce the communication compared to the naive scheme where we actually send the ciphertext in as n ciphertext. And we basically will call this problem as Oblivious Ciphertext compression problem. And Oblivious Ciphertext decompression problem is a similar but related, but it's a slightly different problem where again, we have two parties, client and the server. And the client actually, in this case, holds a plaintext of a vector of a length n plaintext. And again, we have relevant entries, in this case, 5, 17, 25. And the other two, n minus k, are irrelevant entries. And the goal is to basically obliviously send this plaintext to the server in an encrypting way, while maintaining the positions of the relevant entries. But the difference now is that for irrelevant entries actually need not actually be equal when it actually gets to the server and ready to be consumed by the server. And so it can basically be anything. And basically, we want to do this more efficiently than sending n ciphertext, and we basically call this problem the Oblivious Ciphertext decompression problem. So our results is the following. So we only consider the semi-honest setting, and we have our protocols are actually non-interactive and only actually cost a single one-way trip from either the client to the server or server to the client, and it only requires the additive homomorphic encryption schemes. And if we actually assume that the n is a ciphertext length, and k is the number of relevant entries, and epsilon is the compression parameter that we'll actually discuss soon, and lambda the security parameter, then our scheme communication is actually 1 plus epsilon times k compared to the naive n. And the server time computation time is lambda n, and the client time is lambda k. So we're actually ready to now present our techniques to solve the Oblivious Ciphertext compression problem. And again, recall the problem setup where we have two parties, the client and server, and the server holds this vector of length n ciphertext that the client basically wants to retrieve the relevant entries. And so for illustrative purpose, we'll actually assume that all the relevant entries actually occupy the first k positions, and the last n minus k entries are irrelevant. And it's actually easy to extend this to handle the general case where the positions of the relevant entries are actually arbitrary. So we'll actually see that. So what the server and client before execution of the protocol does is they actually agree on a public matrix A of dimension 1 plus epsilon times k by n. For now, the actual exact structure of the matrix A is not too important, but we'll for now assume that the matrix A does not leak any information on the relevant entries indices. So what the server basically does is that it will perform a matrix vector multiplications of this matrix and the encrypted vector using the homomorphic encryption operations to produce the encrypted vector B. And it's actually useful to view this matrix A as a block matrix, where the A1 basically corresponds to the relevant entries and A2 corresponds to the irrelevant entries. And essentially, if you actually carry out this block matrix multiplication operations, then what you essentially get is that the zeros essentially cancel out because they're encrypted as 0. So what you get is that the actual end result is actually A1 times the relevant entry blocks. So essentially, this basically means that the encrypted vector B actually corresponds to this A1 times the relevant entry vectors, which will actually turn out to be useful later. So then after server computing this matrix vector multiplication, we'll send this vector B back to the client. And upon receiving the vector B from the client will essentially decrypt this using a symmetric key and essentially solve the following system of linear equations using the matrix A1 and a decrypted vector B that it retrieved from the server. And if you actually see, as long as the matrix A1 is a full rank, which actually implies a unique solution in this case, then the client will actually correctly recover the values that it wants to retrieve. And this holds because of the equality that we have actually established earlier. So in summary, what we actually get is that the length-n ciphertext is actually compressed down to length 1 plus epsilon times k ciphertext. And this actually only involved the communication from the server to the client, right? And as you can see, if you assume that epsilon is small enough, then this is very effective because the value k is much smaller than kn in this case. And we'll now present our techniques on the Oblivious Ciphertext decompression. And we call the problem setup again. The client holds a vector of length n plaintext with some relevant entries and some irrelevant entries. And the goal is to basically send this to the server obliviously. But in this case, we actually do not care about what irrelevant entries actually end up being with at this point. So this, again, it's actually useful to illustrative for purpose. We'll actually assume that the relevant entries are occupy the first k positions, and the irrelevant entries occupy the last n minus k positions. And this time, the server and client actually also going to agree on a matrix, public matrix A, but this time the matrix is going to have dimension n by 1 plus epsilon times k. And what the client will do, okay, actually first it's again useful to sort of like view this matrix as a block matrix as follows. And what the client will do is essentially basically solve a linear system using the matrix A1 and the relevant entry blocks 5, 17, 25 in this case. And as long as A1 is full rank, then a solution exists. So what the client will then do after obtaining this solution, will encrypt this using its symmetric key and essentially send this to the server. And the server, upon obtaining this from the client, will essentially perform the matrix vector multiplication as follows. And if you actually see what this actually turns out to be, the first k entries corresponds to the entries that the client wanted to send. But the last n minus k, we don't really care what they are. So essentially what the server gets in the end is something that meets the problem requirement. And so in summary, we have a length n ciphertext is compressed down to 1 plus epsilon times k ciphertext. And this involves communication from the client to the server. And yeah, we basically get the similar qualities here. But so far, we have actually sort of like not discussed how this matrix A looks like. And obviously, this matrix A structure is important because we perform matrix vector multiplications and solving a system of linear equations, right? So the question essentially is, we want to basically generate a suitable matrix that admits efficient solution and matrix vector multiplications. And to do this, we'll actually borrow a result from DW19. And we also, in our paper, extend upon the result. And the idea basically is quite simple. So for Oblivious Ciphertext compression problem, what we essentially do is we generate the column by column randomly. But instead of generating like a completely random column vector, what we do is that we only choose like a small window band for each column and generate random entries within that column only. So something might look something like this. And we do something for the similar for the Oblivious Ciphertext decompression problem, but we do this by row instead. And it turns out that if this band length W parameter is sufficiently long enough, then the matrix A1 is full rank with basically overwhelming probability. So we'll actually present some experimental evaluations and applications relating to these two problems. And so we basically implemented the Oblivious Ciphertext compression schemes and using some homomorphic encryption scheme libraries. And essentially, this is basically what we got, where the x-axis is the basically the k value, and the y-axis is the time in seconds to actually perform these operations. And we fixed the epsilon to 0.07 and the total number of ciphertexts to n equals 1.5k. And we did something similar for the Oblivious Ciphertext decompression, and this is basically the result that we get. And so as for the application, it turns out that these two problems, two protocols, have application in several areas of cryptographic protocols, and some of them being single server batch PIR, two server batch PIR, and label PSI, but we won't actually have time to go over this. So interested audience can actually refer to the full paper for details. Yeah, thank you.